All right, let's get restarted. So we now have the first of three tutorials. And at the end of the three tutorials this evening, we have some office hours with experts who can talk about anything, right? The last half hour. All right, so Sean, go ahead.
Okay, thank you. Oops. Okay, yeah, so now I'm excited to give this tutorial on test time scaling for mathematical reasoning. And really the tutorial is about different algorithms for generating outputs with a language model. And so why should you be as excited as I am about this? I think one interesting part is that we'll be able to use what is called test time compute. So compute after a model has been trained to improve the reasoning performance of a language model. So as we saw earlier this morning, as you may have heard about by now, these language models are being used in a wider and wider variety of areas. So ranging from solving Olympiad problems or to things like writing code. And essentially anything that you can frame as a task of generating some sequence are kind of within the potential domain of the language models. And so I'll mostly focus on mathematical reasoning today, but certainly, especially for code generation, a lot of these techniques carry over, and potentially for wider areas even beyond that. And if we think about how language models have been improved in areas like mathematics or code generation, we could really think about it from the perspective of different scaling trends. So the first really exciting trend was scaling the amount of compute used to train the model. So we saw this briefly in the previous talk. But the really striking finding here around 2020, this is from this paper from OpenAI, and they showed that essentially as you increase the amount of compute that's used to pre-train a language model, and so here compute is proportional to the size of the model, the number of parameters, as well as the number of tokens that the model is pre-trained on, you get this predictable improvement in terms of the model's test loss. So here you have this orange line, and this is the scaling law, and it's a scaling law in compute. And so as you increase the amount of compute, you get these predictable improvements in the test loss. So people have kind of pushed these scaling laws further and further, and this has led to better and better models. But at least so far, just doing this hasn't proven to be enough. And so recently, the community has gotten exciting about another axis of scaling, which is called scaling test time compute. So this says after a model has been trained, can we somehow spend compute in order to improve its performance? So here's another plot, and this is again from OpenAI, from late 2024. And now you can see on the x-axis there they have something called test time compute. And as they're increasing test time compute, their model is getting a better and better accuracy on this benchmark. So this benchmark is, again, these math competition problems. These ones are from Amy. And if any of you have used like ChatGPT, now you can access this model through ChatGPT. And hopefully by the end of this tutorial, you'll see some of the underlying technologies that are going on behind the scenes. So this is kind of mysterious, though. How could you possibly take a model that's been trained and then what do I mean by spend compute, and how can you get better accuracy? So there's three main ways that you can do this. One is kind of intuitive strategy. It's you could take your generation model and then you could just try multiple times. So here, let's say I'm trying to solve a problem. Then you could generate many different solutions in parallel. And then you can introduce a separate model which tries to tell like which solution is good, which solution is bad. And then maybe pick the best solution. And so in this in a sense, we're increasing the amount of computation that's being used because we're calling the model multiple times. We're also calling this evaluator model. And so in practice, when you use a technique like this and scale up the number of solutions that you're generating, you can actually see these dramatic improvements um, in the reasoning ability or like problem solving accuracy on these benchmarks. So in this tutorial, I'll go over some of the kind of main strategies for doing this and give you a sense of how you could potentially improve performance further in the future. The second is also kind of mysterious. So we saw this earlier in the talk, and it basically says, okay, you could take your model, and instead of just having it predict the answer to a problem, you could have it generate these extra tokens. And when you think about it, each time you generate a token, you are doing a forward pass through this neural network. And so in that sense, it's spending some compute. And so when you ask a model to generate these intermediate thoughts before an answer, this is in some sense increasing the amount of compute you're using. So again, this has had a surprisingly kind of huge impact in language models and in language model reasoning. The finding that having models kind of generate these intermediate thoughts prior to an answer can lead to dramatic improvements in performance. And so in the second part of this tutorial, I'll talk about this model here, and it can actually let you control in a very fine-grained way how many tokens you're using in these thoughts. And you could see these really nice kind of scaling relationships. So if you only use this many tokens for the thoughts, you get like slightly lower performance, but it's more efficient, and so on. And these kinds of methods are becoming very practical, as I mentioned. Like you can access these thinking models through ChatGPT. You can also run these on your laptop today. So here's an example, and it's an application called LM Studio. So you can download it and install it on your laptop. I didn't create this; it's some third party. But then the cool thing is that you can load in different models that people have developed. Um, so if you make it to the second part of the talk, I'll actually tell you about this model called L1. And this is actually a very small model. And so I've loaded it on my laptop. And now I can have it do something like prove that if x is even, x plus 5 is odd, think for 2,000 tokens. So just to give you, well, hopefully it works. Yeah, there we go. So just to give you a concrete sense of this, if you've never seen one of these before. So here the model is going, and it's basically generating these thoughts, and it's just going on and kind of thinking through the problem, and it's still going. And like I said, this is actually a pretty small model, and you can download it, and it's running on my laptop. And then at the end, after it's done the thinking, it produces the final proof here. And I'm not going to read through it, but probably for something simple like this, even this model on my laptop can do it. So I'll talk a bit about how you train models to produce these thoughts, and we'll see a bit more detail about this. Let's see. And then the third way that you could increase compute at test time is to incorporate other models or tools. So I'll focus on this one a bit less, but certainly a really important and an exciting area where we don't just have a language model, but actually we saw an example in the previous talk, but we have a language model that's calling out to different tools. Maybe you give it access to a code interpreter, um, or you could think of like these evaluator models as being separate to just the language model on its own. And so in today's, just say tutorial, it'll be structured in two different parts. So first, I'll introduce a kind of unified framework for thinking about these test time scaling methods, and it's called meta generation. And I'll go over a couple different patterns that are typically used to at test time. And then in the second part, I'll focus on this really new area, which is these long chain of thought models, like the one that I just showed. So first, let me introduce the kind of framework for thinking about the different test time scaling methods. And it's called meta generation. So first, what is a generator? So a generator refers to using a language model to generate a sequence. So you give it some input, like the proof that I just gave. Then you call the language model and it gives you some output sequence. And you could think of this as like calling some API. You give it an input and then it's calling some model and it gives you some output. And so prior to this excitement about like test time scaling and things like that, there was a lot of research and a lot of work put into how do you just generate one sequence from a language model. And so these will be traditional, they're called decoding algorithms like beam search or temperature sampling, where you're sampling an output from the model. So meta generator.
Sean, I just sorry to interrupt. So as I mentioned earlier, today is a little more free form and more tutorial style. So you feel free to like, stop at any point and stop Sean at any point and ask questions.
Okay.
Yeah, it's not supposed to be a long talk. So yeah.
Okay.
If you have questions, yeah, please come to the mic and ask them. And make sure the mic is on. Go ahead.
Any questions so far? Okay. And so meta generator refers to some strategy for calling this generator multiple times. So I showed you one here where we're calling it multiple times to produce multiple kind of solution candidates. And then we have some evaluator that picks the best one. So there's been a variety of different strategies for doing this meta generation. Maybe I can skip over these based on time or based on what people are interested in. But I'll definitely talk about this first one, which is kind of simple and kind of intuitive, but can lead to really big performance gains. So it's called parallel generation, and it's what I've been showing you, where you have some generator model and you call it multiple times, and then have some aggregator function that picks the final output. So the simplest algorithm of this form is called best of n. And so here what we do is we introduce what's called a reward model. And the reward model is trained to assign some score to, say, like the output solution. Then you pick the one with the best score, so it's called best of n. And so the intuition here is kind of interesting. It's basically saying that if evaluating a solution is easier than generating a solution, then maybe you could train a really good kind of evaluator model. And when you combine it with your generator, the whole system is better than just using the generator on its own. So this is like extremely popular method, and there's been a lot of research going into it. And here's just an example, problem that you might imagine solving. So here you have some input X, you have some intermediate solution Z, and then you have some final answer at the end. And so one question is, what if we actually had a perfect evaluator model and ran this procedure, kind of what would happen? And the results are kind of striking. So what this is showing is as we generate more and more potential solutions with the model, and then we check with this oracle, basically, was the answer correct or not? Some of the models are actually capable of producing correct solutions, um, like 100% for 100% of the problems in this benchmark. And so in some sense, the model is kind of capable of producing a solution. It's just very noisy, so it's not always going to produce a good solution. And so the question is, can we actually detect when one of these solutions is correct or not?
So Sean, I have a question. So the reward model is perfect during the training, right? But not necessarily during inference. Otherwise,
Mhm.
it's trivial.
Yeah, exactly. So this is just showing as a kind of upper bound. This is saying if we had knowledge of what the answer is the model ever producing some solution that has the right answer? Yeah. So then I think as the question was alluding to, the interesting case is when we don't know the answer, can we train one of these reward models and then use it at inference time to kind of choose good solutions? Um, so there's different patterns for doing this. So one way is called an outcome reward model. And the idea is pretty simple. So you have your kind of generator model. You generate many solutions, and then on your training data set, kind of label ones as being correct or being incorrect. And then you just train a language model to predict, um, to classify a solution as basically being correct or incorrect. So there's maybe some nuance in like exactly how you do this, and a lot of it depends on the data that you're training the model on. But broadly speaking, the methodology here is pretty simple. Um, you basically learn to classify whether a solution is correct or not. The second thing you could do is to try to learn a model that predicts whether each step is correct. So let's say you have a really long solution, then the model could predict like, okay, this specific step is actually incorrect. So these are called process reward models, or PRMs. Um, and here you have to think about like, yeah, how do you actually know whether a given step is correct or not so that you could train the model? So the earliest solution from OpenAI was you actually hire a bunch of human annotators, and they look at different solutions and say, okay, like this step is incorrect, and then you get a bunch of training data, and you train your reward model that way. So since then, people have been trying different things to try to automatically get these annotations. Um, but yeah, training a really good process reward model is still a kind of open area of research. Um, but if you have a really good step-by-step model, then sometimes it could be better than just using the model that predicts whether the whole solution is correct. So here's one of the early results from OpenAI. And you could see that doing this best of n with their process-based model um, was better than using the outcome-based one. Um, it's also worth noting that this idea of kind of generating multiple outputs and selecting the best one isn't just restricted to mathematical problem solving. So you can also learn one of these reward models just based on kind of preferences. So here, a human or a user might prefer to have some output that's like not offensive. So you could collect this preference data where a human kind of ranks one output versus another. So you don't have a strict notion of like correct versus incorrect. You just have a notion of like this is better uh, than this other output. Mhm. Yeah. So yeah, with all of these things, the important thing, one really important thing is the data. So again, in a large company, if they're using these preference-based rewards, then they'll typically have human annotators look at actual outputs from the system. You might have multiple outputs, and then they'll rate one as being better than the other. Um, Another possibility is if you have a really good language model, then you could actually use that to come up with preference judgments, and then use that to train maybe like a smaller language model. Um, so then you could think about kind of what objective this is optimizing. And there's this kind of simple argument you can make that when you do this best of n, it's kind of approximating the output that has the maximum true reward. So it's a kind of two-step approximation. So first, it's saying that instead of looking at all possible outputs, you're only looking at these n outputs that you've generated. And then this reward model that you have is kind of approximating the true underlying reward. So this first step is kind of nice because it's saying that as you increase the number of generations or like scale up the amount of compute, then the best of n should get better and better because it's better approximating kind of the search over all possible solutions. But in the second step, you can actually run into issues. So what could happen is that your reward model could be imperfect. And so you can actually start finding kind of flaws in the reward model. Let's say that the reward model kind of latches onto some like spurious correlation. Then if you generate enough solutions, maybe one of the solutions has the spurious feature in it, and your reward model thinks it's correct, but then it's not actually correct. So this is typically called over-optimization, and it's something that actually happens a lot in practice. So here's what's showing what happens if you try to just generate like 3,000 different solutions. What happens is that you start finding these flaws or these kind of exploits in the reward model, and your performance actually starts to drop. Um, so any questions here or things to discuss before I go into the next part?
So, you showed a plot where the process model supervision was doing better than outcome, but I guess it's not matched on the total human annotation effort required, right? Because as you said, process. So if I have a fixed annotation budget, is there some guideline on how I should split?
Yeah, that's a good question. So um, I think in their paper they do a separate analysis where they try to control for that, but it is difficult to control for. Um, I think since that plot, there have been different efforts to create process-based rewards, and sometimes the differences aren't as dramatic. Um, so I guess all I could say is that it does matter kind of how good the annotations are and whether you can get them for your particular domain. Um, but yeah, I don't have like a specific guideline for how you should allocate the budget. Mhm.
Is there a way, for example, to encourage diverse types of strategies to solve a problem? For example, diversity of strategies. So, for example, if one class of pass fails, some other new one succeeds.
Mhm.
And with respect to abstraction, for example, if can the model be trained to think in more abstract and universal principles to so that the proof doesn't get poked holes in it
Mhm.
by someone?
Yeah, those are really good questions. So, um, first, the question of having diverse strategies or diverse solutions. Um, so let me say like two different kinds of approaches. So one is that first you're generating from the language model, and so even the temperature that you use to sample from the language model can actually have an impact on the diversity. So like if anyone has used a language model API, there's this parameter called the temperature, and it basically controls kind of how sharp the or how uniform the output distribution is. Um, so well, one of my PhD students actually looked into this, and we have a paper at ICML showing that based on how the model was trained, different models will have kind of different optimal temperatures. So some models will operate pretty well at a high temperature, some will operate at a lower temperature, and there actually is some optimum which kind of balances diversity with like quality. So that's a kind of low level thing you can do. Another kind of general thing is you can always prompt the model with different information. And that can actually get pretty interesting. So you could imagine like some iterative loop where you tell the model to try some different strategies, maybe some of the things succeed, and then you feed those back into the prompt. Um, and so those kinds of things are, yeah, being explored. Mm.
Like very, very abstract algebra. Nobody knows the whole in the group.
Mhm.
So you can come up trained to thinking like category theory, like very like abstract vision.
Mm. Yeah, that's a good question. I think it's a big question, so I don't know if I have an answer. Maybe two different things come to mind. One is that for the kinds of problems that I was talking about in the morning, this idea of abstraction is really important. You have to kind of break down the problem into these multiple pieces and then try to fill in each piece so that you could finally complete the proof. Um, and so there, I would just say that it's the kind of next problem that people are trying to tackle in the field. Um, the other is maybe trying to control the specific thought process for the model. And this is another, yeah, active area. We have some work on trying to detect different patterns that the model is using while it's thinking, and then you could tell the model like for this given type of problem, use these different strategies, and that can actually boost the performance a little bit. But yeah.
Get the model how the abstract goal state.
Mhm.
The suggestion.
Yeah, yeah, yeah.
Yeah, I think this question is good, and this is precisely why we have the office hour part, end of the day, to have more philosophical slash deep questions. But that's not to say you should stop your questions. Yeah, Giri and then.
So it looks like you're not actually updating the model weights of the generator. You have this outer loop that's driving the test time compute.
Mhm.
Is that ad hoc, or is there some standard where all these updates are captured? Are these where is the learning happening in the test time, or it's lost and every time it's a different?
Mhm. Yeah, so in the first part of the talk, yeah, I'm talking about these methods where you just take a trained model and you have this kind of higher level algorithm, which is just calling it multiple times, maybe calling it an evaluator model, and so on. And so there, it's more that just different patterns for doing this have emerged. So one is this parallel strategy where um, you're calling the multiple model multiple times in parallel, and then the question is like, can you train a really good evaluator model that you could then use at test time? Another case, I don't know if I'll actually go into it, is like tree search, where you can structure this process as a kind of tree search. And then the third is you can kind of feed back in the model's solution so far into its context. So there, the model could potentially learn from its prior failures just through in-context learning. But other than that, for these methods, yeah, no parameters are being updated. I'll talk about the parameter updates in the kind of second part of the talk.
Hi. I saw you used Studio. We use that in our lab too. It's a wonderful tool. Wondering for this next step where you're generating tons of solutions using the model, using Studio, and then you're trying to use reward models. Is there another similar tool that you use to like kind of encapsulate that process at all?
Yeah, that's a good question. Not that I'm aware of. So I think hopefully, fairly soon we'll start to see different libraries for this. There is one called DSPy. So DSPy basically says like these different patterns, like calling the model multiple times and having an evaluator model. You could think of it as a kind of new programming language. And then they try to, give really easy ways to write these like language model programs and optimize them. But I'm not aware of something that's at the kind of level of abstraction as LM Studio. Yeah. Okay. So let me just go over one more of these parallel methods, and then maybe I'll actually jump to the second part of the talk where I'll talk about these really recent reasoning models. So another thing you can do is you could do what's called voting. So here, let's say we're solving a problem and it always ends in an answer. Then instead of just picking the best output, you can basically take votes. So you take like the answer that occurs the most often. So what this can do is it can kind of aggregate information from multiple potential solution candidates, and then you take the answer, that has the kind of most votes for it. What you can also do is incorporate this reward model into this procedure and do weighted voting. So now you can do things like break ties. So like here we have 2 4s and 2 2s. And then what we do is rescore each solution with the reward model, and then take this weighted vote. So again, here you could potentially get the benefits of having a really good reward model while kind of aggregating over multiple paths. Mhm.
Step by step. So, step for the answers generating those.
Yeah, I guess so for the voting procedure, you do need some something to like vote on, if that makes sense. So if you have a multi-step, if you're in a situation where your intermediate steps have some answer to vote on, then you could definitely kind of chain it together. But typically, like in the middle of the solution, you might not have this kind of common answer to aggregate different votes on. And so sometimes you can outperform best of n using this weighted voting. Like here, especially as you're generating more, you can open up this gap. And it turns out you can, or we actually showed this nice kind of formal result, which gives you some insight into what this voting is doing. So you can show that if you take the number of candidates to infinity, then the accuracy that you get will converge to what is shown here. And it's basically the accuracy that you get if you were to sum over or marginalize out all of these different intermediate solution paths. So it's this kind of nice intuition that the voting procedure is, taking into account the information from these different paths. And then here is the reward model showing up. So also the reward model can kind of impact the accuracy that you get. It does mean that since your accuracy will converge to this, that you can't keep doing this forever. So like if you notice in these curves, the kind of accuracy is starting to plateau. And I think what it's showing is that it's basically converging to this thing here. And you can see that the kind of two ways forward then is to actually train your generator so that it's better, so that it kind of pushes up this upper bound. Or you could train a better reward model, and that'll again kind of push up the potential accuracy you can get with the test time method. So this idea of improving the reward model further is itself its kind of own kind of active area of research. So people are coming up with different creative things. Like here, the reward model itself is generating thoughts, and you kind of do this aggregation in the reward model. And at the end, I'll actually talk about some of our group's work where we use these reasoning models to actually evaluate whether outputs are correct or not. So yeah, with these meta generation strategies, you come up with different ways of like calling the generator multiple times and incorporating evaluator models. Maybe next I'll skip to the second part of the talk where we try to train a model with reinforcement learning to kind of search on its own. Beforehand, any other questions on these kinds of things?
It's kind of a general question. Are there like senses where, or cases where by doing like the best voting in the intermediate stages that you actually increase the number of steps that are needed overall? And I guess how does like classic reinforcement learning strategies apply here, or do they relate, or are they different in this context?
Yeah, so I'll talk about reinforcement learning a bit in the second part. I guess like one connection is that you could imagine just instead of having the reward model, training the model so that it maximizes like accuracy at the end of the sequence. But if you have a really good evaluator model that could evaluate whether different steps are correct, then you have kind of more fine-grained rewards. So you could maybe assign a high reward to like the correct steps and then only try to push down the incorrect step. So maybe that's one connection where you could use the evaluator or the reward model. Maybe that's why it's called a reward model, not to just choose sequences, but actually as a kind of reward function. Actually, first I want to mention one more thing, which is connecting with the idea of scaling laws. So it turns out that you can actually make these, you can actually find these kind of scaling laws for these inference time methods. So here, going back to what I was talking about in the introduction, we could think about doing this test time generation as kind of spending compute. And so your compute will depend here on two different things. It depends on how big your model is. And now instead of the number of tokens that you're training the model on, it depends on the number of tokens that you're generating at test time. So then you can ask like, okay, what's actually the best combination? And as we increase the total amount of compute, kind of what are our returns on the performance? So first you can ask the question of like, is it actually better to use a larger model and generate fewer outputs, or actually use a smaller model and use the inference strategy where you're kind of generating more? So to look into this, you could compute empirically one of these frontiers. So what it says is you could try different model sizes, and then you can generate with different compute budgets. So you could have like generate one output, generate 10 outputs, so on. And then for each different model, this will trace out a different performance curve. So then what you want to see is like for a given compute budget, what is the configuration that is optimal for that budget? So we actually tried this out with with actual language models on the mathematical reasoning tasks. And in practice, you actually do see these kind of nice frontiers forming. So this is showing for each line is a different model size. This one is a really small model up here. This one is the biggest model we tested, 12 billion parameters. And then again, what we're doing is using one of these inference strategies like voting and modulating how much we're generating. So at a given point, let's say here we have a compute budget of 128, times 10 to the 11th. And the kind of surprising thing or interesting thing is that for some budgets, it's actually better to use a smaller model and generate more than to actually use the larger model. So this has different implications. Let's say you're trying to have like a model running on your phone. Then there you might have a smaller compute budget than you would have if you have a whole like farm of GPUs. And so potentially you actually want to use a smaller model with a more advanced inference strategy in that case. What we did find though is that to get the absolute best performance, at least here, it's still beneficial to kind of use the largest model and generate as much as you can, which is maybe kind of intuitive. And then since this, there's been, you could think about like, how do you design better strategies that are compute optimal? So I won't go into the details, but in some cases you can use a tree search to do a bit better. And people have also looked into like choosing an inference strategy, even based on how difficult a given problem is. So any questions here before I go on to the second part of the talk? Okay. So next I'll go to these really recent methods called long chain of thought methods. And just to put them in the same framework as before, we can actually think of these as kind of really simple meta generators. So there's this really common pattern, which is you chain different calls to a model together. And it's this kind of like composition of multiple calls. And you could view this chain of thought, I guess it's overloading the word chain, but you could view this chain of thought as being a kind of two-part decomposition. It's saying that, okay, first you call your model to produce some thought. Then you call the model to say like, okay, given the problem and the thought, generate an answer. And as I mentioned before, there's actually been some really interesting work which is looking at a kind of formal level. What is the effect of introducing these intermediate thoughts? And there's been some really cool results that have shown that, well, at a high level, you could think of this thought as kind of adding in some kind of memory where the model can store kind of intermediate computations and then refer back to them later. And at a formal level, this could actually increase the expressivity of the generator compared to just having it try to produce the answer. So another way to think about it is that nowadays we use these transformer models, and a transformer model will have n different layers, and so the amount of computation that you could do in a kind of n layer pass is limited. And when you add in these thoughts, now you have a kind of variable amount of computation that you can do. So then there's a really kind of interesting idea, which is like, okay, if you get this really expressive generation system by just using the thoughts, maybe we can do away with the tree search or calling the model multiple times and just train the model so that it kind of searches on its own and just generates a long thought and maybe tries different alternatives, backtracks, and things like that, just all within the thought. So it sounds kind of crazy, but it turns out to at least appear to work. And this is the kind of key idea behind these recent reasoning models. So the idea is we want to train the model to generate a thought prior to a final output. And then at inference time or test time, we just use a really simple algorithm to just generate an output. And in principle, the model can kind of learn whatever it wants to do within this thought to get a good output at the end. So the common approach for doing this is through reinforcement learning. And the idea here is actually really simple. So what we're going to do is take a model and have a data set of different problems, and we assume that we know the answer to the problems at training time. Then we're going to have the model generate different thoughts. It can do whatever it wants, and then it has to come up with some answer at the end. And then as a reward function, we just check whether the answer at the end is correct or not. So the idea is that the model, through reinforcement learning, can learn whatever it wants, how to kind of productively use the thoughts in order to maximize the reward, which is like getting the answer at the end correct. So this was the key idea behind, if you've heard of this model called DeepSeek R1. And here we're showing this is from their paper. This is showing the accuracy on these math problems kind of improving during training. And what they found is that the response length, so the length of the thoughts, was also increasing during training. So the model starts out by generating kind of short thoughts, and by the end, it's generating thoughts that are like longer than 10,000 tokens. And it's at least correlating with this kind of higher accuracy. So here's an example from their paper, if you haven't seen this before. And here there's a ... so it's actually like extremely long. But these are all, here you start with this think token, and then the model just starts thinking. And then one of the kind of interesting things they found is what they call the aha moment. So the model actually learned to do this kind of self-evaluation or kind of backtracking, where it was taking some strategy and then it said, wait, let's reevaluate this and kind of take a different strategy. So at least intuitively, you could think of this as like, maybe the model has actually learned to kind of internally try out alternatives and backtrack and things like that, just within the chain of thought.
Also found some strange correlations when they just inserted some random weights, right?
Mhm.
When they said weight in random places, the output was also improving. Right?
Yeah.
Did you read about it?
There's so many weird phenomena coming out that yeah, I'm trying to remember that one. Another one is that people found that you can get a large performance boost by just training on like one example. So yeah, people are still trying to figure out exactly what's going on in all of this. One thing is, so this was one of my PhD students, Wei Hua. So he actually went through these different thoughts and came up with these different categories. So here's like 6 different patterns. Sometimes the model shows this uncertainty where it's saying, wait. Sometimes it does this kind of branching or backtracking. Sometimes it's trying to, or at least it appears that it's trying to verify the solution or kind of summarize things that it's done so far. The one thing to remember is that the model is just producing these tokens, so there's no kind of guarantee that this is like actually reflecting kind of what it's what it's doing. But certainly, at least on the external outer level, there are these kind of patterns showing up. Mhm.
If the loss function is just checking if the final answer is correct or not, what's preventing it from doing any gibberish string piece chain of thought, to get the answers correct.
Yeah. So I think that's a really interesting question. So in principle, like the model doesn't have to use language at all. It could like invent its own language to maximize reward. So I think in practice, there's two different things. One is that the model has already been pre-trained on lots of math. So nowadays, the different companies are trying to boost performance on the math benchmarks. So the model that you're starting with before reinforcement learning already has this kind of prior over solutions that are in natural language. Another is like at the technical level, the algorithm typically has this regularization term, and the regularization term keeps the model somewhat close to the original model. So maybe if you remove that, it could actually, yeah, kind of go off and do something much different. But I think it's an interesting question to kind of investigate further. I didn't put the details here, but this is a paper that we just had from a couple weeks ago. I think it was made public. So this is with one of my PhD students, Sungon, as well as a bunch of collaborators. And here they were trying, or we were trying to somewhat systematically look at different patterns that were occurring in these thoughts. So the idea is you generate a bunch of these solutions with thoughts, and then you try to cluster them into different clusters. Here we actually use language models to interpret the clusters. So you, and what we do is kind of contrast one thing against the other. So you say like, is this cluster like inductive versus deductive, or like bottom up versus top down? And then you can have this kind of profile for on this given question or across all the questions in this data set, is the model tending to use like deductive reasoning or top-down reasoning? Is it doing verification a lot and things like that? Now, again, you could kind of be skeptical and say like, is this actually what the model is kind of doing? And I think that's a fair thing. But then one interesting thing is that you can actually use these patterns to improve performance. So the patterns are definitely occurring, and then they appear to be potentially useful. So what we do is we look on a given data set, kind of which patterns give the highest probability of success. And then we just prompt the model to say like, follow a top-down reasoning pattern or use deductive reasoning. And I don't have the details here, but you can actually get kind of performance gains on the different benchmarks. So potentially a kind of future direction is, yeah, how can you better control the model's reasoning, or can you actually teach it different patterns that are useful in different areas?
Acquisition function, like tuning an acquisition function for this can be seen as a Bayesian inference. Each time you try to, in the chain of thought, you try to get a new thoughts based on previous one. Is this like minimizing entropy or loss of information or lack of information? And what you're doing there could be tweaking the acquisition function, be a bit like that. I don't know.
Yeah, I think that's interesting. So, I mean, if you look at the objective that the model is optimizing, it is, in some sense, trying to, yeah, like better compress the outputs or something, and potentially the different patterns that it selects lead to a better compression. Yeah, I guess I would have to think a bit more on specifically how it relates to the acquisition function, though. Yeah.
So I was trying to understand the output there, that where it had weight kind of thing, like where it was kind of seemed to be self-reflecting a little bit. Was there a loop that essentially a self-reflection kind of loop in the code
in some sense, that is like saying, okay, after every step of the thought, you evaluate what has been output. Maybe the model, like asking the model to reflect on the output explicitly versus acting like a token generator.
Yeah. Yeah, that's a great question. So the surprising thing about all of this is that for this, no, there's not. The only reward signal that the model has is the final accuracy. So there's potential different explanations. So one is that actually in the model's training data, it's seen some examples of this self-reflection. Like maybe human solutions actually do this sometimes. And so the reinforcement learning is kind of amplifying that to maximize the reward. Because before these kinds of methods, it's a section that I skipped. Yeah, there was this like explicit self-refinement where you would prompt the model to say, yeah, evaluate this, refine, things like that. Another question is like, well, there's a few different motivations. So one is I mentioned that the model is generating maybe like 10,000 tokens or 50,000 tokens to solve a problem. And so potentially you don't actually need that many tokens to solve different problems. So increasingly this is referred to as overthinking. Or you might actually have a budget constraint. So let's say I'm running on my laptop and I just don't want the model to run for that long and maybe I'm fine with some performance drops. Then what we want is actually the ability to control how long the model is thinking, to have some budget for the reasoning. We've been working on this and we have this method called L1. I should mention that there was a paper before this called S1 that kind of identified this problem of budget constrained reasoning models, I guess. So the key idea that we looked into is, can you just train the model to not just maximize accuracy reward, but also have a penalty for adhering to a given length budget? So basically, now we tell the model, solve the problem, but you have to solve it in 1,000 tokens, or you have to solve it in like 4,000 tokens. And now the model gets rewarded if it solves the problem and if it kind of does it within the token budget. And so by doing this and training the model in this way, you can get this model, we called it L1, which has this kind of nice ability to adjust the token budget. And so here you could see that oftentimes using the longer budget does allow it to solve some more problems. But you can actually get pretty decent performance even with much smaller budgets than had been used before that. So in some cases, yeah, the model is actually kind of overthinking. So this was the example that I showed before in the LM studio. So this again was a fairly small model, 1.5 billion parameters, and everything's open, so you can go and download it. I guess I'm not walking through the instructions on how to download it, but I'm happy to show you later. And now you can use it in a kind of application like this. So hopefully, so this one thought for a while. You could see that the thinking took 23 seconds when I told it to think for 2,000 tokens. And maybe this is a pretty simple proof, so potentially we can ask it to like think for less, like maybe 500. So here it's thinking, and down here it's really small, but it actually thought for 507 tokens, so pretty good adherence to the budget. And then it comes up with some proof. So this area of reasoning models is really fast moving. And since putting out this paper, like a few weeks after, there was a startup that like incorporated this budgeted thinking into their model. Nowadays, the Gemini models and Claude models also have budgets. We don't know how they did it because they don't release the details. But certainly this idea of kind of controlling how much the model is thinking is pretty useful in practice. Let's see. This one, I just want to note that these two different paradigms are kind of, they can be complementary. So even if you have a reasoning model, you can still call it multiple times. And if you have a reward model, like select the best output. So this is showing for like each one of these different L1 methods with different budgets, what happens if you just call the model multiple times and do voting. And you do see improvements still from calling it multiple times. But at least in this setting, it's still kind of beneficial to just generate more tokens in the thought usually. And then finally, this is a recent paper we have which kind of connects ideas from the beginning of the talk and the end of the talk. I won't go into too much detail here, but let me just talk through the key idea. So here what we're doing is we are taking these reasoning models, and instead of using them to solve problems, we're using them to evaluate whether different steps are correct. So essentially, since it's difficult to train these process-based evaluator models using like human annotations, the question is whether you could just deploy one of these reasoning models to kind of evaluate whether each step of a solution is correct or not. So that's the basic idea here. And then the interesting thing is, you could see in the title, it's called Scaling Evaluation Time Compute. Now we have this additional knob we can turn, which is we can actually use more compute to evaluate outputs by having like the reasoning model spend more tokens evaluating the output. And so the kind of cool thing here is that as you scale up the amount of compute that's being used to evaluate the outputs, it actually improves the best of n performance. So here again, what we're doing is we're using the reasoning model to kind of score or detect errors in different outputs. Then we're selecting the best one. And now it's showing that like, yeah, as you use more thinking in the evaluator, it can actually lead to performance improvements. So to recap, in this section, I talked about training a model to generate a long sequence, and then using a relatively simple inference algorithm. And it at least appears that these models can learn something that looks like backtracking or self-correction kind of within the chain of thought. Most of this is happening right now, and every day there's a kind of new surprising thing that comes out with these reasoning models or a new technique. So it's very much an emerging area. And so I'm sure, next year we'll have a much better understanding of it. So that's all that I had for this tutorial. I'd be happy to take questions and yeah, take questions now and then also in person.
Yeah, that is very good. It's at least 20 minutes.
Okay, yeah.
So whoever's asking questions, I'd certainly recommend using the mic or going up to the mic. So I have a question that's a follow-up of what this gentleman asked. It was on my mind as well. To what level have people tried to characterize phenomena that they're seeing as some form of a approximate Bayesian inference or some type of information theoretic structures? So is there any work that is headed in that direction?
Mm-hmm.
I mean, because we need something to pin it down, right? Otherwise,
Mm-hmm.
we're just pointing to phenomena, right?
Yeah,
So.
yeah. There might be. I'm not aware of any, so I would say it's an interesting direction. Because yeah, there's kind of obvious limitations to just looking at the kind of at the surface level what is happening. One thing people have looked into is like at any given position in the thought, can the model predict whether it's eventually going to be successful. And you actually might see this kind of fluctuating certainty that the model, or uncertainty estimate that the model has. So I do think that there is something there to look into, and at least right now, I think it's still an open question.
I think it's probably easier to do in a regression setting where things are better set up. But other questions? I think now is the time to unleash any. Oh, you have one. Yeah. Yeah. No, he's after him. Sorry.
I wanted to ask a question about like connecting this. Like you gave us a very nice overview of how to compose strategies like parallel, sequential. But in the morning you were talking about informal and formal.
Mhm.
So I just wanted to hear your thoughts about like suppose I wanted to have a rigorous proof in the end.
Mhm.
What are the ideas out there? Like should I first do everything using LLMs and then sort of your morning talk about the whole sketching thing?
Mhm.
Or should they be interleaved as I'm sort of building towards a rigorous proof? I was wondering if you had thoughts on that informal, formal bridging.
Yeah. Yeah, so I would say this is kind of going over the different algorithmic patterns, and then you could kind of use these for the problem of going from informal and formal. So an example is like, yeah, when we're trying to do the sketch-based proving, we're actually not just calling the model once, we're calling it even like hundreds of times. And the nice thing is that if you have something formal at the end, then you have a basically perfect reward model, because the formal system is saying, uh, yeah, is this formal proof correct or not? So I think the good setup there is you start with something informal, then you have to translate it into something formal, um, and then you have some kind of perfect reward at the end for whether the formal thing is correct or not. Now, the tricky thing is that there's no guarantee that the formal thing actually is what is in the informal thing. The model can kind of introduce some translation error in there. So that's actually another interesting question. One option is you, as a human, kind of read the formal statement and then you say, okay, this is good. I can kind of trust the proof, and so on. The other is you would have to actually introduce some model potentially to point out errors or point out places to look in the informal proof. So those kinds of things are still, the kind of best pattern is still being figured out. Yeah.
My question will be probably kind of extension of what Kartik asked about. If I'm thinking about, and maybe also in conjunction with another talk in the morning about, well, yes, mathematics-based fields, but not necessarily relying fully on proofs, but also having hypotheses, maybe theoretical physics, maybe quantum chemistry, maybe some theoretical engineering. So looser on requirements.
Mhm.
Yeah, so if you can extend it, that's one part of my question. Another, diffusion models, right? So you didn't mention them at all, and if there is any use of those, and maybe in conjunction with this loser proofs, that will be useful.
Yeah. Yeah, so for the first one, yeah, I would say that right now it's the correspondence with using like a formal system like Lean for math is kind of clear. So I think for other areas, I would think about maybe this idea of using the model and having it call out to different domain specific tools. And then kind of, can you break your problem down into these useful subproblems that the tools are solving? So yeah, I would actually be pretty surprised if like lean proofs is like the only useful tool for different areas like physics or something like that. And I guess earlier we already saw an example of having these more specialized tools, and then the language model is kind of this higher level thing that's calling them. So maybe that's like, from my perspective, the meaningful thing I could say, which is maybe think about it more as like the agent, and then what are the different tools that you want the agent to have access to.
Lean is just a tool,
Mhm.
and we could have some multi-fidelity. A simple physics equation could be a learned verifier. You
Mhm.
know, yeah.
Yeah.
And the second part of this question.
Yeah,
Second, yeah, diffusion models.
Yeah, the second is diffusion. So I really love diffusion. I really like thinking about kind of alternatives to these simple like next token prediction models. Um, and yeah, for a while, I mean, like one of my students was working on the diffusion models, and for a while it was just like the performance was so much worse for text than with the autoregressive models that it was kind of its own separate research question to kind of get them to work as like generative models of text. Because like one key difference with images is you don't have like nice gradients when you're working with these like discrete tokens of text. Um, I would say that recently there's been a lot of advances in diffusion models for text, and so far it seems like one benefit is that yeah, the inference is much different. So here you have a notion of like kind of iteratively refining the output by running the diffusion for longer, and so potentially that could lead to um, yeah, to just new strategies than the ones I mentioned. Another thing is that since it's generating kind of non-auto-regressively, um, maybe you could have like different prediction. Maybe you could have some kind of hierarchical prediction where, yeah, you have the model like generate a structure and then iterate and fill in the details or something like that. But I would say so far it's at least with text, it's kind of too early to say. The main benefit has been that the diffusion models can be faster at inference time. But I think the implications for reasoning is still, I'm still not sure about it.
Real quick question. While conducting your experiments, did you find maybe while doing meta-analysis if certain classes sub of problems from certain fields of math ate up more of your token budget vis-a-vis others? So like algebra versus number theory, etc. Or did you find evidence for there to be a non-human, separation along those lines that you have yet to attribute from like a human standpoint that was discovered in your meta-analysis?
Yeah, so one pattern is, especially on like different combinatorics problems, sometimes they benefit from kind of like brute force solutions. Um, and so sometimes the model will go into these like extremely long kind of chains of like working out different cases, and it just keeps going. Um, and so one thing we noticed is that like just giving the model access to a Python interpreter, it could just write some fairly simple code that just does all that, and you could have a much shorter thought. Whereas in other, uh, yeah, in some of the other math problems, it's not as clear how the code would benefit. Um, so it does even like just as well when it's just using the text-based reasoning. So that would be a very clear case. I guess especially for problems that benefit from some computation, the model could spend a lot of times just manually doing the computation when it's faster to just offload it in some sense.
Real quick, this also is true for like higher order mathematics, like graduate level, beyond, etc. This pattern holds.
Yeah, with that, it's harder to say, I guess, just because it's too early to say. Yeah.
I had a question on the reinforcement learning part, where you were kind of improving the model through checking the final answer. So let's say the answer is actually a little bit more sophisticated, like a proof
Mhm.
in that sense, because I think ultimately the goal was to get to those type of problems.
Mhm.
So it seems like now then you need a sort of a formal checker of some sort that needs to generate the final answer would be, if I'm understanding it correctly, like a actual proof
Mhm.
in a formal syntax. But then if you get that to that point, then the choice of the reward function, I wonder how
how you even choose that, like, or whether it's Boolean, like proof is correct or incorrect, or whether there is a way to grade how close it got to the answer in some sense. I mean, that's true even for the simple math problems to some extent.
Mhm.
Whether that, whether the final refined model is sensitive to the choice of the reward function in that case, like how important is that consideration?
Yeah, so yeah, this is a great question, and it basically connects with like my first talk this morning and this talk, and it's essentially that these reinforcement learning strategies have been developed, assuming that you have this. It's usually called verifiable reward, so it has something that you can check and kind of reliably use as the reward signal. And so for these competition problems that end in an answer, then you could just check the answer. But it's not as clear how that scales to other problems and more sophisticated problems or proofs that don't have a clear answer. So I would say like it's possible that you don't have to use a formal system at all and something else will be invented. Right now, it's not clear what that would be. So I would say that is a potential place where these formal systems would really excel because, yeah, you could basically verify whether a proof is correct or not without having some like final answer. So then there you could have just some binary reward if you want, which is the model starts with some statement, it produces some formal proof, and then it either succeeds or it fails, and then you just have 0, 1.
That works pretty well. The binary reward versus more continuous reward.
So it's what the kind of early works have been using so far, but the kind of fundamental challenges of reinforcement learning are still present. So if you have really long proofs, then like how do you do good credit assignment? And then exploration again. So if you have really long proof and the model, it's like extremely improbable that the model will ever get it, then it's always just getting negative rewards. So those are still unsolved. Yeah.
Talk in the tutorial today. The question whether we should expect one model to be very good at all of those different aspects, the thought generation, the reflection, the synthesis, or if you would expect any performance gain by specializing different models on thought generation and in each of those steps. Would you expect that to behave differently, or would that have its own trade-offs that would make it harder?
Um, that's a good question. So, I mean, one way to think about the thoughts is that they're just some like sequence of tokens that the model's using to maximize the reward. And so in that sense, the model kind of needs to produce the thoughts in order to maximize the reward. I think one area where some decomposition is clear is if the model is like, yeah, again, calling some tool. So again, the model's taking the sequence of tokens, but then some of them are actually calling out to some specialized model. So you might have like a specialized chemistry model. You might even have a specialized like lean model, and then that's been specialized for the separate domain. And then the model sees the outputs from that and then keeps going. And so far that pattern has actually been, I mean, that's been the case. It's like if you look at the lean theorem proving models, the best ones are actually like specifically trained for lean. Or I'm guessing like for these different, you know, molecular applications, it's like ChatGPT is not going to know the specialized domain knowledge. So that's a clear place where this like decomposition, I think, it is happening and will keep happening.
But I think even going back to your question, I think this question may be even more basic than that, right? So even if you're sticking to language,
Okay.
a separate model trained just for thought, right? That was your question, right?
The tool calling is sort of like one.
Yeah,
Mhm.
that's a different issue.
Yeah, it is a version of that though, right?
Yeah.
Like that's a tool that's very good at thinking in a particular pattern.
Right.
Mhm.
That'd
Yeah.
be interesting. Long long reason for models to say, well, this is one, just good at saying, wait, what's something else.
I see. Yeah. Yeah.
Curious how that would affect the performance. So thank you.
Mhm.
So I'm not a mathematician, so I gather like proof checking and verification is an important part of math. Is that like all that math consists of, or also like the hypothesis generating and conjectures? And so my question is, so like in certain cases like combinatorics, or like I saw the Google like circle packing they improved with AI. There the proof is almost the hypothesis as well. And how much does like the proof automation stuff relate to the hypothesis generating or like conjecture generating? And like I don't know what the work in that area is, but I don't know if you could talk about that a little bit.
Yeah, this is a really great question. So so the idea of conjecturing or finding counterexamples is again the kind of next problem for the field to tackle, and it connects with everything. So if we only think about proving a theorem, then to prove a really difficult theorem, you have to think about like what are the actual good lemmas required to prove the theorem. So that's in some sense like a form of conjecturing, or at least like breaking the problem down into different kind of intermediate results. Another is that when we're training the model, we don't actually have that much training data. And so we actually have to get to the point where the model is kind of proposing its own things to prove. So that's a kind of purely machine learning based motivation for having a good conjecturing model, where the model is coming up with new things to prove that are like not too hard and are still interesting. And then the model can try to prove them and kind of improve itself. And then the counterexample finding, I think, is really important in all of this, because to have a good conjecture, when you're conjecturing something, you don't know if it's true or if it's false. And so you don't just want a prover, you also want a kind of disprover to kind of filter out the bad conjectures. So even just viewing it from like a machine learning perspective of we want to build a better system, then this conjecturing is really really interesting, and so is the counterexample finding. And then yeah, when I talk to different mathematicians, I mean this is the kind of key to the process too, where you don't know the answer up front. You spend a lot of time trying to prove something and then find out that it's false, or you actually want to produce it's like interesting to produce a counterexample, and most of this stuff really hasn't been looked into yet in the field.
I have a question with regard to how could one quantify the complexity of a proof, or the degree of compression of knowledge that the model or the thinking model has? Because one of the things that got out of debates between me and some of my colleagues who like to think AI doesn't understand anything, is that generally when the complexity of the model matches the task that I'm asking, the AI appears to understand what's going on. If it's too basic, it looks like it's not smart enough, or if it's too abstract, it looks like it's just a robot punching things. And in general, it's like a free energy principle. You have a budget of tokens, and you have the complexity, and you have the temperature of the model. And if the thing matches well, it really appears that it's quote unquote understanding. So I don't know if you've at any time thought about how to quantify this complexity.
Mhm. Yeah, I mean, I think that's another big question, and especially in the formal proofs, people spend a lot of time trying to think about, yeah, how to kind of quantify the complexity of a proof. So personally, I've only done kind of simple things. So one problem we've looked into is taking one of these proofs and then rewriting it in different ways. So one thing we noticed is that sometimes the proof for like a very simple problem from the language model will actually be kind of long and complicated. So there you could use a very simple metric of just like proof length. Like, can you rewrite the proof so that it's correct, but just shorter? Another thing is we tried to look at the kind of graph structure that is present in the proof. So maybe proofs are kind of more well balanced if they have like multiple subproofs, and then each subproof is only like a few steps long. But at least with those types of things, there's always counterexamples, and it's not clear like what the right answer is.
I wonder, well, and that's a little kind of extension of this, well, Bayesian questions. There are probably many theorems which have multiple proofs, right?
Mhm.
And I wonder if you try to characterize within this framework kind of distribution of all of those proofs, maybe in terms of length, maybe in terms of, well, back to complexity, some additional kind of metric, probabilistic metric
Mhm.
of, developer proofs.
Yeah. So it might be, I mean, it might be slightly different, but yeah, the one thing we have looked into is, again, yeah, since you can have different alternative proofs, then how do you build a system that's not just optimizing correctness, but some secondary quality metric? So one could be length, another could be readability. How do you quantify readability is kind of a hard problem. Or you might want a proof that's more kind of declarative. So it's or one that has like a hierarchical structure. So it has these different it has this kind of high level sketch and then different parts of it. So yeah, one thing we've done is like looked into um, automatically transforming proofs so that they optimize the secondary objective. And certainly there's like, at least in the formal system, many different potential ways to prove a given theorem.
Thank you so much for a nice discussion. First of all, thank you, Sean.
Thanks.
Patient.